Okay, so in this video, we will be discussing on the vector value function. We want to know more about the vector function. Okay, so now just look at the okay. So here vector value function, simply we call that as a vector function, where normally it is represented by the RT. So for the representation of the vector, so if you are using computer to type, so you can use something in bold, okay, which is that is representing vector, or you can have the curly thing down here, or you can also have the cap up here. But the most common one in a written form is this one. Okay, so the vector function in general is represented by RT. T is the parameter, where we have the component x is a function in terms of t, y component there is function in terms of t, and z component there is a function in terms of t. Okay, so f, g, h here are real valued function. For example, we have RT is given by t square, and then we have t plus 1, and then we have maybe 1 over t. Okay, so you have a vector function in terms of parametric, in terms of parameter t. Okay, can we have a vector function in terms of x, y, z? Yes, we have that, but then you can have that particular equation, but the way you want to represent the function is different. Okay, so for your information, if you have a vector function in terms of t, so all the function here are in terms of t, so your graph of the vector function is a curve in space. So what is the meaning of curve in space? Remember, last time you have done the math method one. I didn't teach you, right? But in the math method one, you have the sketching. Remember sketching in 3D? Remember that? And then why you have the sketching in 3D? Because you have two variable function, where you have function z in terms of x and y. Okay, so what is the graph of this function? Firstly, I will say that the function should be in 3D because you have x, y, and z, and then the graph is a surface. Okay, surface. You know what is surface? Surface is anything that you can touch, that calls surface. If something benda lah, benda, bola, baju, that is called surface. But in vector function, if the function is in terms of t, and you still have something in space. Why I'm saying space? Because you have the component x here, you have the component y here, you have the component z here, but the representation of each of the component are in terms of t, so the graph of this is still in space in 3D, but it is a curve, not surface. Okay, what is mean by the curve? Curve is just like line. What is line? Just like tali, rope, you have a thread, benang, a washing line, ampayan baju, that is called curve. Tali lah. Okay, but in space, you can touch it. You can touch the curve. So that is something new for you. You never sketch the curve in space before this, because for that particular function is a bit different. There is nothing to do with the vector function. Okay. As you have in the multivariate function, you have to know the domain and the range. Do you remember that? So the range is the outcome. So the range is the outcome, meaning that the curve, okay, the curve itself is called range. But domain is the condition of the value in the component so that your vector function always real. Okay, so that is a domain. Okay, but here you look at the note here. If domain are interval of real number, okay, so domain here is interval of real number. For example, your domain, so now you have the vector function in terms of t, and then because the inner function here, the function here is depend on only t, right? So then meaning that the domain should be has to do with the interval of t. So let's say t is from 0 to 10. Okay, so if you have that kind of domain, which is the interval of the parameter t, so the curve, just like I said to you just now, the curve is representing a curve in space or space curve. Okay, but back to the what is mean by the domain. Domain is input. What is the condition of the input so that the output always 0? Okay, so that is the idea, the same idea that you have learned in math method 1 about the domain and the range, but this one a bit different because your function is a vector function, but the idea should be the same, but we apply on the different kind of function. Okay, so if your domain or region in the plane, okay, then your vector function represent surfaces in space. Okay, so meaning that your vector function is, you have r in terms of x, y. Okay, so that is your vector function, but not in terms of t. Okay, region in plane, meaning that plane on xy plane, right? Or on zx plane, or maybe on zy plane. So here your region is on, your function is in terms of xy. So the vector is, maybe I will say x plus y for the component x, and then for the component y we have x squared. Okay, and then maybe I will say x squared plus y squared. Okay, so the domain is depending on the value of x and y. So then what is your graph of this particular vector function? So you must have surface. Okay, the first one just now, if in terms of only interval of t, so you must have a curve in space. But if your function is in terms of x and y, in terms of variable, then your graph of the vector function is surface. Okay, now look at this kind of vector function. Now you have the vector function in terms of parameter t. Okay, so this one is for component x, and this one component y, and this is for component z. Okay, now we look at one by one. For the x component, okay, for the x component, so the equation is ln t. So now again, back to the domain that you have learned in math method 1. What is the condition of t so that the value of x always real? So t must be always positive. So that is the condition. Okay, now for the component y, you have t over t minus 1. So you have the fraction form. Okay, so here the t at the numerator, there is no condition, right? But however, the t minus 1 here cannot be equal to 0. So the condition comes from the t minus 1 cannot be equal to 0. If you have 0, then y does not exist. So in order to have y always exist, so we put the condition here. Or you can rearrange, so you can see that t cannot be equal to 1. Okay, and then z. So component z, you have a minus t. Is there any condition for this particular equation function? No, there is no condition, so it can be any t. T is always real number, but because of uh, these three components will join together, will give you the value of the r, right? Then you have to combine all them and the condition all together here to be an interval. Okay, so how can you determine it? Okay, so what I'm doing is I'll just list down the line, the number line. So this is 40. Okay, so this one negative infinity and this one positive infinity. Okay, so the general one, we can have any t, but however we set here t cannot be equal to 1, so there is the constraint. So this one is 0, so this is 1. Okay, so cannot be 1, so it's stop here, right? Because you cannot have the t equal to 1. But then from this one, t always positive. Okay, so t always positive, so this one is 0, but t cannot be equal to 1, so meaning that you can cut this one. Okay, we don't want this. Okay, so the possible interval, we just focus here. So the possible interval always lying in this interval and also in this interval. So we can rewrite the t is is t can be 0. Is there any condition t can be 0? Is that t okay, here from the first one here, t cannot be equal to 0. Okay, so we cannot use the equal sign, so t is from 0 to 1. So also we cannot have t equal to 1, so that's why here we don't put the equal sign. And then t, the second interval, is we can put 1 to infinity. Okay, so this is the first interval, 0 to 1, and then 1 to infinity. So because of that, we can say that the domain of the given function is the interval of t. So because of our domain is in the interval of the parameter, so we know that the curve of this particular, the graph of this particular vector function must be a line in space.